Okay, class. Good afternoon. So this is another topic in power plant engineering. So this is performance of diesel power plant. So the presentation in the performance of diesel power plant is presented maybe in several parts. Okay. So let us consider an illustration of a diesel engine. Okay. So you will notice that here in the illustration, if you look at the figure, the mass of fuel will enter the combustion chamber. So since diesel engine is a compression ignition engine, the air of course is compressed to the combustion chamber or to the cylinder, or the mass of air will also enter the combustion chamber. Another here is the cooling water. So cooling water is of course very important to be circulated inside the engine in order for water to absorb the heat, of course, generated inside the engine or combustion chamber. So another, of course, here is the lube oil. So in order for the rotating parts uh, to eliminate some friction from the rotating parts, it requires lube oil. And the lube oil also absorbs heat, of course, coming from the friction also. Okay, so the mass of the exhaust, of course, will also goes out. Of course, the mass of the exhaust is the summation or the mass of the air plus the mass of the fuel. Okay? So, let us now proceed to the energy carried by the mass of fuel or carried by a fuel. So, the energy carried by the fuel is so-called the energy chargeable. So, where that energy chargeable is equal to the mass of the fuel injected inside the combustion chamber, of course per hour, multiplied by the heating value of the fuel rather. Okay? So take note that the power developed inside this combustion chamber is called the indicated power. And of course, the indicated power will be reduced to brake power because of the friction inside the cylinder and the rotating parts of the crankshaft. So we have here a mechanical efficiency in between the indicated power and the brake power. So the brake power now is lower than the value of the indicated power. Okay. So the brake power now will be delivered to the flywheel of the engine. And the engine or the generator rather will receive brake power, and the power developed by the generator is called electrical power. Okay? So let us now proceed to the heating value of the fuel. So heating value of the fuel is equals to 41,130 plus 139.6 degree API. So the unit here used is an SI, that is kilojoules per kilogram. So solving for degree API if not given. So degree API is equals to 141.5 over specific gravity or specific gravity at 15.6 minus 131.5. Okay. So, if we want to determine the specific gravity at 15.6, that is equals to 141.5 over 131.5 plus degree API. And the specific gravity at temperature T. So, that is equals to specific gravity at 15.6 multiply 1.0007 minus T times 15.6. Okay? So, determining now the indicated power. Indicated power is equals to indicated mean effective pressure multiplied by the length of stroke, area of the bore, and the number of power stroke per minute divided by 60. Take note, the unit here is in SI. Okay? So, where IP is the indicated power in kilowatts, PMI is the indicated mean effective pressure in kilopascal, L is the length of stroke in meters, area of the bore in meter square, not meter, and N is the number of power stroke per minute or power strokes per minute. That is also equals to 2 can over S, where C is the number of cylinder, A is acting, so A is 1 for single acting, A equals 2 for double acting. And N is the number of RPM, and S is the stroke. So, for 2-stroke engine, S is equals to 2, and for 4-stroke, S is equals to 4. Okay. So, indicated mean effective pressure. If the engine utilizing an engine indicator. Okay? So, the mean effective pressure indicated, of course, equals to the area of the indicator card multiplied by the spring constant divided by the length of indicator card. And PMI now is equals to area times spring constant over length. Okay? So, let us now take this example. So, in order to apply the formulas above. Okay. So, let us take now this example. A 6-cylinder 4-stroke engine has a bore of 110 millimeter and a stroke of 120 millimeter. When running at 640 RPM, an indicator card is taken which has an area of 420 millimeter square and length of 60. So, if the spring constant is 129 kilopascal per millimeter, determine the mean effective pressure and indicated power. Okay? So, given PMI, so the area of the indicator card is 420 millimeter square, and the spring constant is 120 kilopascal per millimeter and 60 millimeter square or millimeter length. So therefore, the indicated power or the PMI rather, indicated mean effective pressure is 840 kilopascal. And then substituting now this mean effective pressure to the original equation of indicated power, and therefore the indicated power is 30.7. Okay? So, another, we have the brake power. So, what is a brake power? So, simply the brake power, of course, is the power output measured at the crankshaft by a dynamometer. Okay? Or flywheel power. Okay? So, that is the same. So, where BP now is the brake power, so in kilowatts, BMF is the brake mean effective pressure, length of stroke, area of the bore, number of power stroke per minute, number of cylinder, acting, number of RPM, and stroke. So, these are all the same to the what is written in the previous slides. Okay? So, we have also determining the brake power in terms of torque. So where this torque can be determined using a dynamometer or a prone brake. Okay? So if we take a look at the illustration here, we have a prone brake or mechanical dynamometer. So we have here L, or meaning this is the length of the arm. F is of course the net force, and then a lever arm, and then the wooden blocks. Okay? So of course, if the bolt of the dynamometer is tightened, the flywheel will of course be gripped with the brake shoe installed inside or at the wooden block. Okay? So the torque now can be equals to F net is equals to F gross minus F tear. So what is this F gross? So the F gross is the force measured by the weighing scale. And the F tear is the weight of the brake arm. So we have to deduct the weight, or of course, weight of the brake arm. Okay? So taking again another example. So in determining the brake power, so this is now the example. A single acting 4-cylinder 4-stroke cycle diesel engine with a bore to stroke of 22 and 28 cm operating at 275 uses fuel with 28 degree API. The load on the brake arm, which is 90, and the length of the arm is 90, and the load is 120 kilogram. What is the brake pin effective pressure in kilopascal? Okay. So the given, so we have here to determine the piston displacement BD, so that is equals to LAN, the length of stroke, area of the bore, and the number of power stroke per minute. So the computed value of the piston displacement now is 0.09757 cubic meter per seconds. Okay? So the torque now is equals to F net multiplied by R, where F net is equals to 120 kilograms. So changing this 120 kilograms to kilonewton, so multiplying it by 9.81 divided 1000 times 0.9 is equals to 1.05948 kilonewton meter. Okay. So the brake power now, or the brake mean effective pressure, from the brake power formula. So brake power formula is 2 pi Tn over 60. So the brake power is 30.51 kilowatts. And determining now the brake mean effective pressure if brake power is given and piston displacement. Therefore, substituting values, the brake pin effective pressure is 312.71 kilopascal. Okay? Thank you very much. This is now the end of my presentation.